Now, we want to look at solving ODEs with Laplace transform. That's ordinary differential equation with Laplace transform. We're looking at first order, second order, and then non-homogeneous. So the first equation here says y prime of t plus y of t equals exponential 2t with condition that y of z is equal to 0. Now, we will transform all these things using Laplace transform. We don't need to be showing working here as we have been doing. We just need to be solving, just use the formula we had already and be putting there. We don't need to be showing how we got it. Y prime of t is same thing as f prime of t. So just take it as f prime of t. So when you do it, y prime of t will be sy of x minus small y of 0. Just like you had when you did your y. You had that Laplace transform of f prime of t is something as s f of s minus small f of 0. The same thing we just did here. So Laplace transform of y of t, small y of t, is capital Y of what? S. So you come down and replace it. Replace this with this. That's how where you have this. You have this now. That's this thing now. Will give you this. Why am I having 0 here? The reason is that y of 0 is 0 from this place. You see, man? So replace y of t with capital Y of s. That's the Laplace transform. Then exponential 2t. If you have this, the Laplace transform from the formula says you have 1 over s minus 2. S minus what? 2. That's Laplace transform of exponential at is 1 over s minus a. So now our a here is what? Is 2. Having gotten this now, we want to find a way to make capital Y of s the subject of the formula. And how do we do that? We are going to factor out y of s from here. Normal equation form, you can do this one, it's so simple. So when you bring out y of s, and you have just s, this s now remaining in the brackets, and then 1 from this side now, because you have 1 y of s, so 1 will remain in the bracket. So you have this equals to 1 over s minus 2. That's this part now. So to separate this s minus s plus 1, you know you have to divide both sides by s plus 1. If you do that, you have this. Next thing, we're going to use partial fraction to decompose this fraction now into into as many as possible fractions we can get. But in this case now, because we have two linear denominators, partial fraction demands that we use a method of this form, where we'll be having each factors or two denominators being on separate separate places. So you have a over this over this. You can actually solve this, but let's do it together. So what do we do here? We are going to multiply all through. That we multiply here by the LCM of all these things. The LCM is this one now. This is the LCM. This is the LCM. Multiply here by this. To cancel out, we have 1 only. Multiply this one, this place now, by this. S plus 1 will cancel out. We have what? S minus 2 only. You see, by a bracket s minus 2. The same thing goes to the other one. We have this. So we want to get our a and b. If I want to get my a and b, I can decide let s be equals to s be equals to minus 1. That's the safest way of doing this. Or let's start with let s equals to 2. Yeah. To get our b, we need to eliminate a by setting s equals to 2. When you put the 2 here, you will have 0. This will give you 0. If you put 2 here, you have 2 plus 1, 3. That's 3b. And then 1 equals to 3b. So if you now solve, that's what you have here now. 1 equals to 3b. If you solve it, you have your b equals to 1 over what? 3. 1 over 3. So set s equals to minus 1 in this case now. If you put minus 1 here now, here, you end up eliminating b. If you put minus 1 here now, you have minus 1 minus 2, that's minus 3. Minus 3, that's what you have here. Minus 3. And remember there was a 1 here. So you now solve it, you have what? A equals to minus 1 over 3. You see, when you divide both sides by minus 3. So we have gotten our A and B. I can now go back to this place now and replace my A and B. My A is minus 1 over 3. My B is 1 over 3. You see, I can as well put it into other places. But this thing, just to make it easier for you to solve, that's why it was outside, it's put outside like this, so that it will be clearer what Laplace transform we are doing here. Because now we'll be doing what we call inverse Laplace transform. Remember, this thing has already been transformed using Laplace. That's why you are seeing the S. To take it back now, we need to apply inverse Laplace transform. Now, from the table, it's always exponential that gives this type of thing, s plus 1 under here, s plus something, whatever. Now, if you want to go back now, this thing will mean exponential minus 1t, because what is here is 1. Remember that this thing here now normally comes from that exponential coefficient. So because we have 1 here, it will be exponential minus 1t, you get. Then because we have minus 2 here, it will become exponential 2t. So remember, these numbers are still here. These numbers are still here. This one is still here. So this is the Laplace transform of that thing. And this is our final answer. So we have gotten our y of what? Our y of t. If you want to check if you are correct, you can replace your t by 0. Because if you put 0 there now, it's expected that you have your y of 0, because that t, when you put t as 0, it means y of 0. So you put 0 here, put 0 here, you're expected to get 0. Just as you were given that time now. At t equals to 0, y of 0 equals to what? 0. So that's how you check, you get your answer to know if you're right or not.